All right, so I just wanted to go through the problems from problem set 3 that I assigned in class today to help you guys out. I think it could be useful to maybe see a couple examples worked out. So the first type of example here that I'm going to do in number 4 is the angled launch that's on a flat surface. So here we have the Eagles kicker steps onto the field for a kickoff. The ball leaves the kicker's foot, moving 25 meters per second at an angle of 47 degrees above the horizontal. And so it asks us for 3 things. How long is the football in the air before landing on the ground? How far away does the football land on the ground? And what is the max height achieved by the football? So you want to, visualize this. Our player is here. And he is going to kick the football from here, and it's going to travel upward and then back down until it lands over here. What they're telling us in this problem is that it's leaving his foot at 25 meters per second. So if we draw a vector there, the 25 meters per second is the magnitude of that vector. And then the angle that we're at here is 47 degrees. So the angle it makes with the horizontal. And just based on these 2 pieces of information, we're able to determine a bunch of different things about this projectile motion. So the first thing we want to figure out is how long the football is in the air before it lands on the ground. So whenever it hits the ground here, what is the time going to be equal to? In order to do that, what we're going to need is the initial speed in the y direction. We need the initial y component. So if I think about this vector here being components, I have some component here in the x direction, which we call vx. And I have another component here in the y, which we'll call vy. And more specifically, we're going to call this viy, because this is our v initial, our initial velocity in the y direction, or in the up direction, in the y hat direction. Okay. So we can break this vector of 25 meters per second at 47 degrees into the x and y components simply using our equation for sine and cosine. Vx equals vi cosine 47. Well, we'll put in the equation first, cosine of theta, and then vy, which in this case is going to be viy. The reason I don't put vix, again, I talked about this in class, but the reason we don't put vix here is because we're assuming acceleration in the x direction is 0. And so there is no such thing as an initial x velocity and a final x velocity. The x velocity is constant. So it doesn't make sense to denote it as vix and vfx when we can just say vx. But the y value does change, so we do need to denote that as viy or v final y. And this is going to be vi sine theta, just like that. All right, so you can go ahead and plug these numbers in. You're gonna plug in 47, or sorry, oops. You're gonna plug in 25 for the vi, 25 your magnitude, cosine of 47 degrees, and same thing for viy, but it's going to be 25 sine of 47 degrees. All right, and you can plug these into your calculator and get numbers. Let's see, what do we get here? All right, so we get 25. Sorry, 25 cosine 47. That should come up. Make sure your calculator's in degree mode. But plug that in, and you should get 17 0.0, and 0.49, so it would be 0.05. And for the other one, 25 times sine of 47 gives 18.3. It's 18.28, so we'll round it to 18.3. Okay, so these are both in meters per second, and voila. All right, so it's looking good so far. Now, we want to figure out the time at this final point right here. And so what we're going to do is we're going to watch as the ball travels through the air. The VIY component is actually going to become 0 right here at its max point. And then it's going to start to actually increase again. Well, sorry, it'll continue to decrease into negative values, but the speed will begin to increase as it picks up speed as it falls toward the ground. And when it hits this bottom point here, the vector here is equal to negative VIY. So this is the key. This is really the key to solving this problem. And there's another thing you can do. You can set delta y equal to 0. So if I wanted to, I could I could set delta y equal to 0 because my y direction displacement didn't change. If I look, I started here and I ended here, and so my height values are the same. All right. So I either use negative VIY for my V final, or I use delta y equals 0. One of those two is what I need to solve this problem. And what I'm looking for is time. And so I'm just going to use the equation. I'm going to use this one here. And I'm going to use the equation that V final y equals V initial y plus AT. And I'm gonna be looking to solve for time here. So my V final is just going to be negative 18.3. My V initial is positive 18.3. And my acceleration is negative 9.8. As it has been in all of these problems, acceleration in the y direction is negative 9.8, and time. And so when I solve this out, the negative 18 gets subtracted over, so you get negative 36.6 divided by negative 9.8. Negatives go away, and you're left with a positive 3.7 seconds. And that's your answer to part A. All right. So we found the time that it takes to get here. How far away does the football land on the ground? So here it's asking for our delta x value. Let me use, we'll use this blue here. What I'm looking for is basically this distance here. What is this delta x? How far did the football travel in the x direction? And this is actually really easy to figure out. So I'll do it right here, part B. When we're looking at the x direction, there's one equation that we use in all these problems. It's always Vx equals delta x over t. You don't have to remember all the other kinematic equations when we're working the x direction. And this is always the case because acceleration in the x is 0. The horizontal acceleration is 0. There's no air resistance, no friction that we're considering. So we're assuming that, we're kicking this ball and it's traveling through a vacuum, essentially. So all I do is I use my value for Vx from here, and I plug it down into here, which gives me 17. And delta x is my unknown, so I leave that as delta x, and I plug in the 3.7 seconds that I just found here. And so I'm going to do delta x equals 3.7 times 17, which is going to give me the 62.9. That's the answer for that part. All right, and then finally, in part C, let's go ahead and switch this again. We'll go to purple. All right, so in part C, now we're going to be looking at the max height achieved. So we want to figure out how high did this kick go? What was my delta y whenever it's at the top here? Notice now I'm not talking about this delta y when I'm here. I'm talking about the y when it's at its highest point, at this point up here. And what you have to realize about this is, well, the time that it takes for it to reach here is actually half the time that it takes to get all the way down to here. So this 3.7 seconds that I calculated in part A, I can't use that. But what I can do is I can use half of that as my time. And so, you just take 3.7 and divide it by 2, and you end up getting 1.85. That is your time. So this right here, the time at the top is 1.85 seconds. And that's what you're going to use for your time in part C. And you can use the same v initial y of 18.3. We can use this time and we can use acceleration, and you can figure out delta y. That equation would be delta y, let me use purple here. That equation would be delta y equals vi yt plus 1/2 a t squared. Now that'll work. The math on that's not too bad. You'd plug in 18.3 times 1.85 plus 1/2 9.8 and then 1.85 squared. And you would get 17.1. Now there's maybe an easier way to do this, and it's to consider the fact that also at the top here, your y direction velocity is 0 when you're at the top. So Vy equals 0 when I'm at the max height. And so if I actually do the equation of V final y squared equals V initial y squared plus 2a delta y, this might be easier to solve. You can do this either way. You can do it this first way here, and maybe I'll show the math down here for that. So let me show you what I would plug in for that one. So I'd be solving for delta y, and let's draw a little arrow down here. Okay. Where was it? Yeah, solve for delta y there. So I'm going to plug in 18.3 for VIY. I'm going to use half the time, so that's 1.85. I'm going to add to that the 1/2, the negative 9.8. The negative sign there is super important, and then the 1.85 squared again. Okay. And when you plug all that in, you'll solve it, and you'll find that delta y is 17.1. Okay, so not bad. This works. But you can also look at it in regards to this equation with v final y being 0. And this might be a little simpler to solve. We put in 18.3 squared plus 2 negative 9.8. And then delta y's are unknown. Room here. Okay, so in this case, you would square the 18 first, divide it or subtract it over, and then you would divide by 2, divide by 9.8, and you'll still get the same delta y value of 17.1 meters. So again, 2 ways to approach that problem. Both should give you the final correct answer. All right, so that is an example of the horizontal launch, angled launch, flat to flat. And I'm just going to do one more problem here with the horizontal launch. And that should be good. Okay, so number 5 says a giant boulder is rolling 8 meters per second toward the edge of a horizontal cliff. The boulder rolls off the cliff and lands 22 meters from the base of the cliff. So it's our classic physics problem where we have, maybe we've we've got this cliff here, and maybe, we've got this giant rock, and for some reason the rock starts to roll off the cliff, and it's going to crush all the little people below. Oh no, run away. It looks like some guy already has a problem, and now he's good. And these guys are all like, what's going on? They're scared, maybe. I don't know. Now it looks like he's protesting or something. I don't know. Okay. Maybe they are protesting. I don't know what they're protesting about. Maybe they're protesting about the rocks falling on their town or something. Anyway, we don't know why the giant boulder is there. What we want to do in physics is is we want to talk about what's going to happen to this boulder when it rolls off the cliff. So, it comes down here and it's coming down and it goes whoop. Let me get rid of that arrow. It comes down and it takes this path downward, and maybe that's why he's scared. All right. Well, all we know about it is that it lands 22 meters from the base of the cliff. And it's rolling 8 meters per second. So we know the value of this vector. If I look at this as a vector, the initial, it has 8 meters per second in the x component and 0 meters per second in the y component. And this is very crucial. That's the first crucial step. So it's different than the one we just did, right? We just did this problem where I broke them into components and I found the x and the y by doing the sine and cosine. In this problem, it's already given to us in components. It's already given to us as 8x plus 0 y hat. All right, so the boulder rolls off the cliff. It falls 22 meters, and we want to know how long it takes before it hits the ground. So when it hits the ground here, what is its time? And if the boulder was in the air for this long, what's the height of the cliff? In other words, what's our delta y? So those are our two unknowns that we're looking for in part A and part B. You can think of this as being the second part of the projectile motion. This is just the downward descent. So just like our kick went up and then came back down, now we're just looking at the part where it comes back down. So as I said in this example, Vy is 0 at the top. Well, Vy is 0 at the top. It's still 0 here. But now what we're going to be doing is we're going to be looking for the time it takes for it to get to the bottom where it lands. Very, very common misconception that I hear a lot is, well, okay, so when it hits the ground, Mr. Sherrick, isn't its final velocity going to be 0 because it's coming to a stop? Well, what we're really concerned about is right before it hits the ground, how fast is it going? Obviously, yeah, after it hits the ground, it'll roll around a little bit, it might bounce, and then eventually it'll come to a stop. Don't do this. This is bad. All right. I'm just going to scratch it out. Bad. All right. Don't do that. It's like BAP. Okay. Bad like my handwriting. So don't do that v final y equals 0. It does not work. The v final is going to be a positive value, or sorry, it's going to be a negative value as it hurls toward the ground. This velocity vector, if we were to look at it, would have these two components again, Vx and Vy, and neither of these is going to be 0. All right. But that's fine. We actually don't need this v final y. All right. What we actually have to do in this case is look at the x direction first. Because I know that I'm kind of getting stuck in the y direction. Well, I don't know v final y. I don't know time. I do know v initial is 0. And I do know acceleration is negative 9.8 meters per second squared. But I don't know what delta y is. So none of my equations will work. I have 3 unknowns. I count them 1, 2, 3. So my y direction, I'm actually stuck. So it's time to look at our x direction and figure out what we can do from there. So the x direction is always very simple. It follows one equation, and that is Vx equals delta x over t. Always, 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 always. This is your x direction equation. And again, this goes back down to the fact that we're assuming no air resistance. We're assuming no x direction acceleration. So what is Vx? Well, Vx is going to be the 8 from our initial horizontal speed. This is why it was important to write it like 8x hat and 0y hat. The 0 here, that tells us our VIY. The 8 here is what's going to tell us our Vx. All right, so we've got 8 equals delta x, which is 22, divided by our time. So we can very quickly do the math. Multiply both sides by t. We get 8t equals 22. Divide by 8 on both sides. 8 goes away there. 22 divided by 8 is 2.75 seconds, and that's our time. Okay, so simple enough. In part B, we're looking for if the boulder was in the air for this long, 2.75 seconds, what was the height of the cliff it fell from? So now, look, I can now put in 2.75 here. And so now I have enough knowns. I have time, I have VIY, and I have acceleration, and I want to find delta y. And so now I just have to pick the equation that doesn't have VFY, which is going to be this equation here, delta y equals V initial yt plus 1/2 at squared. Right? I'm looking for delta y. VIY is 0. Why is VIY 0? Again, it comes back from this factor here. The fact that it says that the boulder rolls horizontally off the cliff. All right, it's coming off the cliff horizontally, and that's very, very important. So we have a 0 there. 0 times t is 0, so 0 times 2.75 is 0. We're going to write that in. We got 1/2 negative 9.8, and then we've got t squared, 2.75 squared. Make sure when you're plugging this into your calculator that you do the exponent here. Don't square the whole thing. Do the 2.75 squared first, and then multiply it through by 1/2 by 9.8. And you should end up with the answer of 37.1 meters. All right. And you're actually going to get a negative answer from this. The question asks, what's the height of the cliff? Delta y is negative because you start at a higher height and then you land at a lower height. And so your displacement in the y direction was negative, but the height would be a positive 37.1 meters. If we were to, want to match our solution exactly. All right. So that's it. Hopefully this was helpful. Yeah, I'll see you all tomorrow.